Good evening, everyone. It's my pleasure to welcome you to the fifth and final installment of the Community Science and Technology Special Virtual Seminar Series, Demystifying COVID-19, presented by Pacific Northwest National Laboratory. This session is being recorded, so those who are not able to join us today can view it at a later date. My name is Jim Sanford. I'll be your moderator again today as we hear the last presentation of this exciting 5-part series designed to share what we've learned and answer questions related to the global coronavirus pandemic that has affected us all over the past year. Before we get started, we'll go ahead and flip over to our usual polling feature to get an idea of where people are joining us from today. Please click on the link in the chat window provided to take you to the poll. You can participate with your computer or a mobile phone, and as you enter your answers, we'll see the results start populating the screen in real time. Take a few minutes here to give everybody a chance to visit that link and start typing their locations in. Excellent. Seeing some results pop up. A reminder that PNNL has a primary campus located here in Richland, Washington, but we do have locations in Sequim and Seattle, Washington, Portland, Oregon, Maryland, and Washington, D.C. So it's great to see most of those locations represented here. I personally have friends and family that I've told about this in Ohio, Indiana, Tennessee, Florida. So I'm gonna have some phone calls to make if I don't get some representation there. But it does look like we've got a nice cohort from around the Tri-Cities and around Washington and Chicago, San Francisco. Excellent. Take just a few more seconds here to let any last answers trickle in. Okay, well, thank you everybody for participating in that one more time. Typically, this is where I would take a moment or two to describe PNNL's role in advancing the DOE's primary missions and economic impacts in the communities where we live and work. Do want to streamline a bit as I have the last couple of weeks. So I would again encourage you to watch the first 2 talks where I went into a little bit more detail on some of those metrics. You can also visit pnnl.gov to get some more information in that regard. However, I would like to highlight ways in which Battelle and PNNL strive to be good stewards in the community and communities where we live and work. One of those mechanisms is this Community Science and Technology Seminar Series. There will be a link provided in the chat to the PNNL events page, which will have information about upcoming talks, as well as a link to the Demystifying COVID website, where you can find the recordings of all the previous talks and this one in a few days. Our regular series are talks given by PNNL scientists that focus on the world-class research taking place right here in the community. But as I hope you're familiar with now, this is the tail end of something different where we've put together a 5-part seminar series focusing on various aspects of COVID-19 science. We're on the last of our 5 PNNL researchers who have volunteered to give presentations on the indicated topics today. Each talk has been outstanding so far. I do hope that everyone has been able to attend the previous 4, and if you have and have filled out the surveys at the end and they're on your 5th and final one more survey to go and you will get a digital certificate of completion. So far, we've heard great talks from Stephen Wiley, Amy Sims, Katrina Waters, and Kristen Omberg. Again, I hope everyone was able to see those. If not, the link that's in the chat to the Demystifying COVID website will have those recordings posted. Today, we're going to be hearing from Tim Shibey, who will be discussing epidemiological modeling of COVID-19, what types of models exist, how they're developed, how they're used, and how they might help predict our future. I'll introduce Tim in just a moment, but let me first do one more reminder of the format of the presentations. Tim will speak for 25 to 30 minutes, after which we'll jump into a Q&A session. I encourage you to type questions that come up throughout the talk into the chat window as you listen along. These will be collected and presented to Tim at the end. We've had great questions coming through, big numbers. We've been able to answer a few more as we've added 15 minutes of extra time to the Q&A session. So I hope that we have quite a lot of input again tonight. And tonight at the very end, following the Q&A, we will have a quick closeout session where the members of our community panel are going to have a moment to summarize what they've learned and are taken home from this seminar series. So again, we are joined by our panel of community representatives. They've come prepared with some questions to spur the Q&A session later. Let me take a moment to introduce them. So far, I believe Kate McAteer is the only one I haven't introduced first, so let me go ahead and start with her. Kate is the Vice Chancellor for Academic and Student Affairs at WSU Tri-Cities. Kate?
Thanks, Jim. So I'm really interested in this talk tonight and hoping to learn about how we in education might be able to use these models to really develop a more robust in-person learning experience for students in the fall.
Cool. Me too. I think that you'll find something very useful in here. Next, we have Justin Raffa, the Artistic Director of the Mid-Columbia Master Singers. Welcome, Justin.
Hi, Jim. You know, this term flatten the curve has become very common parlance over this past year, and initial COVID safety responses in our state projected a need for a 2-week shutdown in order to achieve that flattening. So I know myself, like many others, are wondering today, were we indeed successful at flattening the curve? How many curves did we flatten, and do we anticipate any more curves in the future?
Excellent, excellent. Next, we have Martian Valedez, the Regional Director for Heritage University's Tri-Cities campus and the Interim Executive Director for the Tri-Cities Hispanic Chamber of Commerce. Martian, what are you looking forward to hearing about tonight?
So I'm looking forward into the future a little bit and looking how models can help us better understand this idea of herd immunity, and in particular also herd immunity given the different vaccination rates, right? So there's, I guess, a general herd immunity, but given the different vaccination rates here, even just here with Kennewick, Benton, and Franklin County, how that might impact our communities and how we can make a transition to be safer in the future.
Thank you. Yes, those are certainly topics and questions on everybody's mind. Finally, we have Loanne Ayers, the President and CEO of United Way of Benton and Franklin Counties. Loanne?
Well, you know, I work with small businesses and nonprofits every day, and modeling has now become part of our normal language, and yet there's still a lot of misunderstanding. And so I'm really eager to learn to demystify modeling and bring it down to the language of the normal person so we can better understand how we can prepare future contingency plans for our businesses and our organizations.
Perfect, thank you. Well, you're at the Demystifying COVID seminar series, so I do hope that you'll be satisfied with what Tim's going to share with us tonight. Thank you again to our representatives for attending. Look forward to talking to you in the Q&A session. Without further ado, it gives me great pleasure to introduce Tim Shibey. Dr. Tim Shibey is the lead scientist for PNNL's River Corridor Scientific Focused Area Project. He develops the scientific vision for multi-scale and computational science within the Environmental Molecular Sciences Division and frequently offers a national perspective on future scientific and technological needs. He specializes in multi-scale modeling, including parameter estimation and mitigating uncertainty. He obtained his PhD in civil engineering from Stanford University. Welcome, Tim. Take it away.
Okay, thank you, Jim. I think I'm going here, so let me see if I can get back to my, okay, great. So thank you all for joining. I really appreciate the good turnout tonight, especially given that we're head-to-head against the Gonzaga game tonight right now. Thanks for joining, and I really look forward to talking about modeling today. But I wanted to start with a poll and ask you all, when you hear the word model, what comes to mind? The word modeling has a lot of connotations. So if you can follow the link in the chat and start entering your words, we'll see them appearing. We're starting to see some already. Glue, building models, predictions, pretend, mathematical, example, data. Those are all great answers. Representation. Obviously fashion models like Cindy Crawford. Okay, the runway, excellent, good. So I'd like to also know then, have you heard of these COVID related phrases? A number of them have already been mentioned. And so I'm curious about how much you know about these phrases. The first one is flattening the curve. Have you heard the phrase flattening the curve, and do you have a sense of what that means? And again, I think we're going to get the poll in the chat. Okay, there it is. Good. wait a little bit for some things to come in. We're maybe having some trouble with that link according to the chat. So I'm going to, in the interest of time, move to the next one. If you've heard the phrase herd immunity, do you understand the phrase herd immunity, or have you heard that phrase? Again, here's the poll survey in the chat. Getting some yeses in the chat, and this phrase was mentioned. All the questions should be coming through, I guess, in the same survey. So we're getting about 2/3 saying yes here. And finally, the basic reproduction number. This is something we'll talk about in the course of describing models. It looks like a few more people have questions about what is a basic reproduction number. And so again, with that, we'll move on. Thank you for answering those questions. Today's discussion, we'll talk about a few particular components of this graphic that you've seen if you've been at the previous talks. And we'll specifically be talking about how people move from these different states, from being susceptible to infected to infectious and immune. And so we'll use a number of different terminologies that we've talked about again over the past 4 weeks. I'm going to particular focus today on transmission, which is really how does a disease spread from person to person within a community? And then of course, we'll talk a lot about models. A model here being a representation of a disease or a disease process that can recapitulate the key aspects of that disease. And I'll give you a little bit more description of what I think a model is. In fact, I'll start with that now. So hopefully demystifying the idea of what a model is. A model is, in my view, an approximate representation of a complex system. And it's an approximation that we use in a variety of ways. We can use it to learn about that system. We can use it to encode our knowledge of that system. And hopefully we can use it also to predict the behavior of that system into the future. So when we think of models, there's many different kinds of models. So I'm going to start with thinking about me as being the reality. And here's a photograph of me. What kind of models might there be that describe me as an approximate representation that we can use in these various ways? So one might be a fashion model. And I might use a fashion model to learn about or to predict what I might look like if I wore certain clothes. Of course, it's an approximate representation because I don't actually really look like this guy. And so it's only an approximation, but it might help me understand what I would look like in that suit and tie. I would have an anatomical model that might tell me something about, or it might encode our knowledge about how our body is structured. So where different organs are and what they look like. And that may help us learn about the body as well when we teach in a classroom setting. We might use a laboratory model to subject it to tests that we might not want to put onto humans. So for example, what would be the result of exposure to a chemical, or what might happen if we use a certain drug? A mouse is obviously not a perfect model of a human, and yet it has many human attributes that do make it useful as a model for testing of things that we don't want to immediately test on humans. And finally, of course, I can have a computer model which embodies mathematics of a system and can be used to describe how a person might interact with their environment, for example. There are many different types of computer models. We can also have simple descriptive models. So somebody might tell you, well, Tim Shibey is a nerdy scientist who programs computers. And even if you don't know me, you might have an idea about what that brings to mind in your universe of models. I'm going to argue today that all models are wrong, but some are useful. And this, in fact, is a very famous phrase amongst modelers that was first published by the statistician George Box. The idea of this is that all models are approximations of reality. None of them are actually true, and yet we can use them in many helpful ways. And so hopefully today we'll talk about COVID models. But first, I'd like to say that the kind of models that I actually mostly work with are actually physics models, mostly having to do with hydrodynamics, the flow of water and its impacts in natural systems. And so some of the models that I actually use in my everyday research are shown here on this page. This is a model of flow through a porous sand and a model of flow in rivers in the Columbia River Basin. So the question for tonight is, can we use mathematical models to learn about, to encode our knowledge of, and to predict the spread of diseases like COVID-19? Again, keeping in mind the definition of what a model is, and keeping in mind the idea that all models are wrong, but some are useful. So we'll start out with a very simple mathematical model, and I'll share a couple different types of models with you this evening. We'll start with a model called the R0 model, or we could call this the R0 model, the way we speak about this, a large R with a subscript of 0. So to introduce this model, I'm going to refer you to an analogy and ask, have you ever heard about the power of compound interest? If you think about this example case, I have two people here that I'm going to use in my example. Both of them, Dontrell and Alicia, both saved $1,000 a month starting at age 25 until they were 35. And then they stopped putting money in that account and let those accounts grow over time until they retired at age 65. Now, the interesting thing is Dontrell's account had a 5% interest rate, and so it gained at a rate of 5% per year. And Alicia's had a slightly higher, only 2% higher, of 7%. But that very small amount of difference in interest rate, when compounded over many years, led to a very large difference in the amount of money that they had at the end of that time period. In this case, in this example, Dontrell has about $700,000 in his account at the end of the at age 65, whereas Alicia has almost double that, over 130,000. So this is the power of compound interest. The R0 model, or the R0 model, is really the very similar model to the compound interest model. And R0 is defined as the basic reproduction number, that term we talked about in the poll. This is the average number of new people that are infected by any one infected person. So let's use an example again. Dontrell had COVID-19, and let's imagine that he spread it to one other person in his home. Whereas Alicia had COVID-19, but she quarantined very early and didn't spread it to anybody else. Let's say Olivia had COVID-19 and she spread it to 2 other people before she became symptomatic and quarantined. And then Brandon had COVID-19, but he never got symptoms. He was what we call asymptomatic. And unknowingly, without even knowing he had the disease, he spread it to 6 other people. Now, if we average that out, we add up 1 plus 0 plus 2 plus 6, that's 9, and we divide by the number of people 4, we get an average of 2 1/4. Each person on average spread it to 2.25 other people, and we call that our R0. And our simple mathematical formula for this model is here. It says over a time period of the disease spread, which in the case of COVID is maybe 5 to 7 days. So if we take the time period at the beginning of a week, our current time, we multiply it by 2.25, at the end of the week, we would expect to have that many new infections. And so that simple model can tell us a lot. We can learn from this model that, like compound interest, a very small change in this R0 value leads to a big difference in the number of infections. So if I run this model out for a couple examples, let's assume I start with 100 infections at time 0, and I have an R0 of 1.1. This model tells me at the end of 10 weeks, I'll have about 260 infections. That's the rate of increase of infection under this particular model. However, if I increase the R0 value slightly to 1.5, meaning that each person, instead of average transmitting it to 1.1, they now transmit it to 1.5 people, you can see, again, I've plotted the blue curve here for reference, going from 0 to about from 100 to about 260. But I'm also showing now a new curve for 1.5, which goes from 100 at time 0 up to almost 6,000 cases after 10 weeks. So a very small increase in the number of average transmissions leads to a very large change in the total number of infections over time, because these infections build on each other in the same way that compound interest does. This points out to us then the importance really of reducing that transmission as much as possible. Even very small changes in transmission of the disease can lead to a big change in the number of infections. And in fact, we can show that if our R0 is less than 1, ultimately the pandemic would be controlled. If we can reduce the average number of infections from one person to another to below the value of 1, the total number of infections will go down eventually to 0. Now we can think about a more complex model. In fact, there are a variety of different very complex models. I'm going to introduce a slightly more complex model called the compartment model. This model, we basically think about people as being in 3 different possible states. Either a person is susceptible to the disease, or they're currently infected with the disease, or they have been infected, but they're now recovered and we assume immune to the disease. Okay, and we want to program our model in such a way that we describe the rate at which people move through this pattern from susceptible to infected to recovered. We have here above the arrow between S and I, a mathematical formula that describes the rate of how fast people move between those two pools. And really, it simply says that the amount of people becoming infected depends on how many people were previously infected, how many people were previously susceptible, and this little parameter we call R, or the infection rate parameter, the small lowercase r, which is related to the big R naught that we saw before. And that really just is kind of common sense. The more infected people you have, the faster the disease is going to spread. The more susceptible people you have, the faster the disease is going to spread. But it's also going to depend on how often those infected and susceptible people interact, which depends on a lot of other societal factors, like how much are people practicing social distancing and so forth. We also have a rate that describes above the other arrow how fast people move from the infected pool to the recovered pool. And really, this only depends on the number of infected people and the average speed at which people recover. So if it takes people 14 days to recover, we can estimate this parameter theta, we call the Greek letter theta, which is the recovery rate parameter. Now, using this very simple mathematical model, I actually programmed it up into an Excel spreadsheet. It's very easy to program this model. Let's consider a hypothetical example and see what we can find out. So imagine a very simple problem. A small city of population about 10,000 people in a remote location, perhaps like Sedona, Arizona, which is the city pictured here. Imagine that one of the residents of Sedona went to Phoenix and was exposed to COVID-19 early in the pandemic. And then they came back to Sedona. How could that one infection affect the city over 1 year's time? Assuming, and this is obviously an oversimplistic assumption, but assuming that no COVID-19 was brought in again from anywhere else, how would that one infection affect the city? If we apply our model that we just described, where the total population is 10,000, the initial infection is 1, and we model the time period of 365 days, I'm going to use these model parameters, and we'll describe a little bit more later of what those parameters mean and how I got those numbers. But if I use those model parameters, these are actually the plots that I get, the results of my model. And what I'm showing here is on the x-axis, the number of days since the beginning of the pandemic, 0 being the time of the first infection, 365 being 1 year. And on the vertical axis of my graph, I have the total number of persons represented by these plots. And here in our case, the total number of persons in the city is 10,000. And so as you can see, we start out with 10,000 susceptible people, those are the blue, actually 9,999. And we start out with one infected person down here near the 0 point, and that's the orange curve. And as we go forward in time, the number of infections increases and the number of recovered people begins to increase, but it lags behind the infections because it takes some period of time for that recovery to occur. We also notice that the infection increases until the number of susceptible people drops quite a lot. And once the number of susceptible people drops enough, then the number of infections starts to go down because there's not enough susceptible people to continue the spread. We can also notice that the number of susceptible people, even though the number of infections ultimately goes back down to 0, the number of susceptible people doesn't actually go to 0. It's the idea that once the number of susceptible people reaches a small enough level, the spread can't continue in that community. There's not enough people to be passing it to, and therefore we've reached what would be called herd immunity, in this case at 97% infection. 97% of the people have been infected and recovered. 3% of the people never got infected, but the spread of the disease has now stopped. Herd immunity isn't a single number. This 97% is just for this particular example and for these parameters, but we'll see how the herd immunity might change under different scenarios. What else could we learn from this model? Well, what would happen if we changed the infection rate? Our old infection rate for the previous model I just showed was this value of 0.000025. What if I set a new rate, which is somewhat smaller, of 0.000015 instead? This might reflect less contagious conditions, such as reduced interactions through social distancing, or a reduced amount of virus spread because of mask wearing and personal hygiene, or perhaps simply a virus that is less transmissible than we initially assumed. The insights here is we did what we call flattening the curve. We can see that the peak is both lower. In the initial model, we had a peak number of infections of close to 4,000. Here we have a peak number of infections of about 1,700. And so the peak is lower. It's also later. It comes, instead of at 60 days, the peak comes at about 120 days. And interestingly, if we plot the whole set of curves as we showed before for this particular example, this is our new prediction of infection. And you can see in the orange curve is our infection. And you can see that we've reached zero infection with a much higher level of total not people that are still susceptible. In other words, herd immunity has been reached in this case with less total infections, about 83%. Because we have less contagious virus or conditions that lead to less spread, we've been able to control the virus with a lower number of people becoming infected, which of course is greatly beneficial in terms of strain on the healthcare system and the long-term impacts of the people who have been infected and possibly deaths of people who have been infected. So you're probably asking yourself in your mind, well, if we can just change the parameters and get a different result, what are the correct parameters for our model? And this is really a very difficult question, of course. Initially, we have to base the estimates of our parameters on prior knowledge from experience, for example, with other diseases like flu viruses or other coronaviruses that we know of, or maybe the MERS virus or the previous version of SARS. One thing we do know is if the recovery takes, let's say, 14 days on average, and you've all heard, people should quarantine for 14 days, then we can estimate this rate parameter as being 1 in 14 or 0.07. So that's where that number comes from. And if we have an estimate of the basic reproduction number, we know the relationship between the basic reproduction number and this little r value as a function of the total number of population and the recovery rate. And so we could calculate that if this R0 number was 3.5, if the average person transmits to 3.5 people, that would equate to a small r value of the value that I used in my initial example. Now, as we start to get into the pandemic and we start to learn some new information, what we can do is we can begin to fit the model to early data and modify our parameters, getting a better idea of what the true parameters should be. So here in this graph, what I've shown is a blue set of blue lines here down in the lower corner, which represents some hypothetical data. So assume that we had some measured, tested cases, and we knew that these cases occurred. You can see that these data are noisy. They go up and down from day to day. But on average, I can fit a new model through the orange curve here through those blue data and say, well, now a better estimate given the data that I have of my transmissibility might be this new R value that I show here with a 0.0000185. And as we get more and more data, we can further refine our model to match the observations. This process is called calibration or parameter estimation, and is a key part of every model that we tend to simulate. Now, what if we think we might have an idea of maybe the range of those values? Maybe we don't know the exact value of our R parameter, but we think it's larger than, it's probably not larger than this and probably not smaller than that. Well, we can then calculate our model for a range of different parameters within those bounds, and we can use that then to give us an envelope of predictions. And this is how you'll often see the model data presented, where there's a sort of an envelope of possibilities with sort of a best guess somewhere in the middle. And so with this, I'm going to ask us to look at some real model data. So far, we've been playing around with this toy model system. But as a modeler, back in the early days of the pandemic, I was very curious to look at what the model predictions were saying, and also to begin to track them over time and see how they panned out. And so I actually started taking some screen snapshots on my phone of a particular website that showed current data as well as forward predictions into the future. And this is from the URL that's shown in the lower right-hand corner of the slide. And so on April 1st, for the state of Washington, the noisy curve here on the left side is the number of deaths that were measured up until April 1st, observed related to COVID. And the dashed line is the projection forward in time, the predicted number of deaths in the state of Washington. And the pink envelope shows that particular model's estimates of the uncertainty range. So it could be as high as 60 in the peak, or maybe as low as, maybe as low as 20 or 25 in the peak. And so as we move forward in time, and a week later, I took another screen snapshot, and we see that there'd been a large number of deaths occurring in the state, but a lot of variability from day to day. And that we can see that it's still following pretty closely to the initial prediction, and that the uncertainty bounds maybe have reduced a little bit as we've gotten more data. But the peak, the potential peak, is still perhaps as high as 45 or so. And as we move forward in the future, we see by April 19th, we've actually passed the peak of the first peak of deaths in the state of Washington. And it turns out that that peak value was close to 45, about 42 deaths in one particular day. But it still is tracking fairly closely with the initial curve. And you can see that that envelope of uncertainty is diminishing over time. But we also see that it predicts that it should go down to close to zero by mid-May or early June, which, as we all know, didn't actually happen. So if we look at the real data over the course of the past year, these are the deaths in Washington due to COVID pandemic. And you can see that first peak early on that I just showed in the data, and it's going down. But instead of going down to zero by June, it of course flattens out. And then we see a second peak in the summer during 2020 of August. And we see a third peak, a much stronger peak late in 2020 and early 2021. And this is really due to the fact that our model represents one single community. But of course, what happened in Washington is that much of the early spread was in Western Washington. And it wasn't until later in the year that it began to spread in places like Yakima and the Tri-Cities and Spokane. And so maybe we're seeing the superposition of multiple first peaks coming through here. But we're also seeing the fact that people maybe early on in the pandemic, we had very strict rules and people stayed at home for 2 weeks. Whereas later on in the pandemic, people started going back to work. People started, not wearing masks as much and so forth. And then, of course, during the summer, we had this second peak, and then finally this third peak, which people think is probably due to, families getting together over the holidays a lot more and much more gatherings. And now we're back down into a lower range currently, although some indications are that we may be headed for a possible fourth peak soon. Now, another kind of model we can look at, and this is an interesting type of model, is to simply look at statistics from the past. So if we look at the total number of deaths in each week in past years, in this case going back to 2013, we can calculate an average number of deaths for each week of the year. And we can also estimate what's sort of the upper boundary of the number of deaths for each week, given what we've seen in variation from year to year statistically. And that's what this plot from the CDC shows. The green are the actual number of deaths observed, and the orange is the estimate of the maximum number we could expect due to just natural variability from year to year. And so what we see is this concept of excess deaths. Anything above this orange curve is considered to be unusual number of deaths for that week, given historical trends. And one of the things we see is that this first peak in January of 2018, we see some excess deaths. And we know that in that particular winter, there was a very severe flu that caused about 60,000 deaths in the US, which was a high number for the flu. And so most of those excess deaths were due to that particular flu outbreak. And as we move forward here and we start looking in early 2020, January, February, March, we start to see again excess deaths occurring. But in this case, we can label many of those excess deaths, as shown in blue, as being COVID observation deaths. And it actually tracks quite well. If you look at the curves, you can see that the excess deaths match the early curve in April, the secondary peak in August, and the third higher peak in December and January. And so again, we can learn from the statistical model. It gives us some assurance that the deaths that we're labeling as being COVID related are in fact related to COVID and not some other cause of death, because they're very anomalous compared to what we've seen in previous years. And it turns out that the number of excess deaths is very similar to, or slightly larger than, the number of deaths that have been attributed to COVID in the US, suggesting that perhaps we're actually slightly undercounting the number of COVID deaths, or maybe there are other causes of death related indirectly to the COVID pandemic that may not be showing up directly as COVID-related deaths. Now, one of the things we do as modelers is we have to think hard about what our assumptions are. And we've got a lot of assumptions built into any model. In the simple model that we used, we're going to explore a number of these assumptions. The first assumption is that the rate of infection, in this case, our parameter R, is a single number. But of course, we know that that's not really true. It could vary over time because public behaviors change, policies change, maybe the virus mutates, or it could vary within a given population between different subpopulations. So people that live in large families, or people in assisted living, healthcare workers, essential workers. But here in this case, I show with my simple model, what happens if I change R over time? Maybe R starts out low, gets really low during a stay-at-home period, but then goes up as we relax restrictions on public activities. That gets reflected in a predicted model curve that shows multiple peaks, similar to what we've seen in the actual data. And so as we learn more about the disease, we can begin to understand how these transmission parameters are changing over time due to public behavior, due to policy, perhaps due to mutations and other things. Another assumption we've made in fitting our model to our data is that our testing data actually represent all the infections. And as we know, that people with mild symptoms may choose not to be tested, or tests may not be available. In fact, early in the pandemic, we know that it was very hard to get tests. And so early on in the pandemic, the number of confirmed infections is much lower than the number of estimated infections when we account for testing not being available, or asymptomatic cases where people never get tested because they never showed symptoms. And so we have to account for all of those possible situations when we try to match our models to the data that we have. Another assumption that's inherent to the model that I presented here, which again could be in other models, is that recovered persons are immune. In this case, we know that immunity from having the disease might be weak. In fact, we have seen rare cases of reinfection of a person that previously was recovered from COVID. We know that immunity may only last for some period of time, but we haven't really been into this long enough to know how long that immunity might last. Is it years? Hopefully it seems to be more than months, maybe at this point, but it might not be many years, or it might be a long time. And new mutations and strains that are coming around might not be susceptible to the antibodies developed to the initial strain, which could then cause us to have to add to our model a pathway that would allow people to go from the recovered pool back into the susceptible pool, and they could eventually become reinfected. I'd like to ask this question: can models predict the future? This is what a lot of people would like to know. And the answer to that question is, of course, it depends. Depends on a lot of things. How well are the underlying processes understood or known? Are our assumptions all valid? Are the important factors in our disease transmission model represented? How well do we know our parameters? How much data do we have, and how uncertain are those data? So think of a couple examples. Here on the upper right, I have a picture of SpaceX Crew Dragon docking with the International Space Station. And thinking about that, it's kind of incredible that a rocket launched from Florida, flying around the Earth several times at thousands, tens of thousands of miles per hour, can somehow dock up to a tiny little space station that's also orbiting hundreds of miles above the Earth at tens of thousands of miles per hour. And yet our NASA engineers can model that very precisely, such that only very minor adjustments are needed by the astronauts in order to allow them to dock exactly with the space station. In that case, a model is extremely accurate and very predictive. But in the case of, say, weather phenomena like Hurricane Katrina, we have models that predict where this hurricane is going, but you've all seen that they would typically have an envelope of prediction because there is some question about how accurate those models are going to be. And different models give different predictions. In the case of Katrina, most of the models predicted it would go across Florida and then turn sharply north and hit the Florida panhandle. But one model in particular predicted it would go further to the west and hit New Orleans, which we know now it actually happened. So by considering that uncertainty, they were able to try to evacuate a larger area of the coast than they might have otherwise if they only considered what most of the models were saying. So I would argue that a better question is, can models help us learn and support good policy decisions? So when we think about flattening the curve, applying social distancing and masks to reduce our transmission parameter R, we can reduce the total number of infections over the course of the pandemic, and of course the deaths associated with those. We can achieve herd immunity at a lower level of infection. We can reduce the impacts on our healthcare infrastructure, and we can, importantly, as Steve mentioned in his initial talk, we can limit the number of infections and deaths while we're in the process of developing vaccines or other therapies that will help us. And speaking of vaccines, vaccines would dramatically change our model, because now we can actually reduce the number of people in the susceptible pool without increasing the number of infections. We break this model chain of arrows from susceptible to infected to recovered, and we now go directly from susceptible to recovered or immune by having a vaccine. So this model really clearly drives home the value and importance of vaccines. Asking the right questions of our models might reveal new data or information that we need to collect. For example, if our data and our models are not really matching up, we might question, well, are we not really getting the right test results because of asymptomatic spread? Or what is the possibility of reinfection or the impact of new variants? Now, in addition to the models that I've described so far, which are epidemiological models, there are a number of other kinds of models that are also relevant to COVID-19. For example, hydrodynamic models, which can help us understand the spread of aerosol particles that carry the virus within certain environments. On the right side here is a model of a supermarket showing how a person who sneezes that's infected, how those particles can be transmitted from aisle to aisle, or can be actually taken out of the system by a good ventilation system that goes out through the roof. So in summary, I'd like to share with you some modeling best practices. These are things we think about as modelers, whether we're modeling COVID or whether we're modeling flow in a river or whether we're modeling a hurricane. We have to understand what are our assumptions and how do they affect the model output. So we think hard and long about those questions. We want to test our model solutions and verify that our code is working the way we expected it to. We want to realize that our model predictions in most cases are inherently uncertain. There are questions about how good they are. We have to consider alternative models with alternative parameters and interpret the results accordingly. We have to understand that our data themselves may also have errors or assumptions inherent to them. And finally, I think the most important one is updating the model and parameters as new information and data become available. One of the things people have often been frustrated about through the pandemic is that predictions seem to change over time, or maybe guidelines seem to change over time. But in fact, predictions of models should change over time. As we get new information, we should be updating our model and our predictions. And it's really not surprising that predictions made with very little data initially might not be that good. We can use our models to learn and to guide additional research and data collection. And then working in teams to assure that the best information and methods are used is really critical. Openness, sharing our data openly, sharing our models openly so that they can be reviewed and tested is fundamentally important. Again, reminding ourselves that all models are wrong, but some can be useful to us. So thank you very much for your attention today. I look forward to discussing your questions with you, and I hope that that's been informative for all of you.
Great. Thank you, Tim. That was a wonderful talk. Appreciate all the time you're taking and all the information just conveyed right there. We have about 150 people that have joined us tonight. And there's been some questions circulating up through the chat. So let's jump right into the question and answers. As I mentioned at the top, we're going to start with our community representatives. Came prepared with a couple of questions. So let's start with Kate. Kate, do you have any questions for Tim?
I do. Thank you, Tim. That was a wonderful presentation. So I've seen a couple of models for college campuses, but they seem to all be based on residential most students living on campus. So for colleges in our community, like CBC and WSU Tri-Cities that are commuter campuses, is there just too much variability, or is there a model out there that we could look at for our fall plans?
Yeah, thank you for that question. You're right. I think most of the models of transmission relating to universities and colleges are focusing on residential campuses where most of the transmission actually happens on campus. However, some of those models do have a transmission pathway from non-campus interactions. So one model I found suggests that there's a 25% chance each day that one of their students becomes infected by transmission from a non-campus contact. That's actually a very small number if you think of only one student possibly getting infected. But that number would presumably be much larger if you have a non-residential campus where most of the interactions are occurring off campus. So you could really modify that model by changing that parameter. Again, you'd need some data to help you understand where is the transmission occurring, how much of it on campus, how much off campus, what are the situations your students are living in off campus, and how does that affect the transmission rates. But if you had some information and data to support that, or at least some speculation about those things, you could make some model predictions that would help you understand.
Thank you.
Great, thank you for the question, Kate. Next, we'll move to Justin. Justin, do you have any thoughts on Tim's talk or a question for him?
Tim, to your knowledge, what are the most reliable and critical sources for following the latest COVID models? Is it the CDC, World Health Organization, others? And similarly, what are the indicators of credibility? Or contrary, what are the red flags we should watch out for when sifting through these COVID-related models?
Yes, thank you. Thank you for that. I think, the CDC, National Center for Health Statistics, has a lot of data. I showed some of the data. For example, the excess deaths chart was from that. I think that's really interesting if you're curious about statistics that you might not hear about in the news. I also look for sites that are affiliated with well-established research university programs such as Johns Hopkins University, or the University of Washington has an Institute for Health Metrics and Evaluation. That's where I showed many of the models that I showed of real data for Washington State. They're at the site healthdata.org. In terms of red flags, I would definitely question any information published on social media without double checking it. I think most of us know that. When you're looking at those kind of information, it's important to read materials from multiple sources because, often data can be presented from different points of view. So getting different points of view and information. For example, going to the CDC website and look at excess deaths really helped me to have a sense of confirmation that COVID deaths were in fact being counted correctly, although there was a lot of dispute about that in the news. When we're looking at scientific papers, we want to be careful about not putting too much emphasis on preprints that haven't yet been peer reviewed. There's a lot of early publication of preprints. Those are important to learn about the latest research, but we need to take them with a grain of salt until they've been properly peer reviewed and vetted. So those are some of my thoughts on that. Thank you.
Thank you.
Thank you, Justin. Okay, we'll move to Martine. Martine, do you have a question for Tim?
Yes, and thank you for the great presentation, Tim. I appreciate it. So as you may know, Franklin County has one of the lowest vaccination rates. And, I've heard I was talking to somebody from the health districts, and they said a lot of it has to do with the fact that we have a smaller population of folks over 65, which is helpful for the future. But in terms of modeling and given sort of the disparate vaccination rates and infection rates in the bi-county region, how can models help us predict what may happen in one over another? Or can we predict, how the Latino population, for example, in Franklin County is going to be impacted similarly or differently from, it's porous, right? We're right across the river. We're not self-contained. So is there a way to model that? And also to use that data to convey the importance of vaccination to the community?
Right. Yeah, I think, the importance of vaccination can, if you kind of understand that, even if you don't know about the model per se, but you understand the idea that people move from being susceptible to being infected to being immune, and that really vaccination breaks that chain. If you think about being able to become immune without having to go through the disease and all the potential risks associated with that, that's really a huge thing. And so, Obviously people have concerns about risks with vaccines, and those are not invalid concerns, but the huge benefit associated with that is so large that I think encouraging people to not be one of those people that has to go through that infected pathway. It's not only good for them individually, it's good for the community, because the more people we get into that, out of that susceptible pool, the less spread is going to happen in our community, the less chance for mutations of the virus, all of those things. And so really, it's about thinking not only of your own health, but also the health of your community and of your family. We do know that there are inequities amongst different populations that lead to different incidences of infection. And so we know, for example, people in minority groups that might be disproportionately represented in some essential work settings. Maybe it's grocery stores or farms or things where they can't leave their job if they're at higher risk of exposure, or maybe they live in more crowded or multi-generational family conditions. So all of those things could lead to higher disease transmission. And so a more sophisticated model would actually account for subpopulations and use different transmission rates for those. And we definitely have seen, also in the case if you have lower access to healthcare or insurance, that might lead to poorer outcomes for those people that do get infected. So these things are all really important considerations and things that models by other people have taken into account.
Great, thank you very much.
Thank you, Martine. Okay, we'll move to Loanne.
Tim, early in the pandemic, there was pretty significant public distrust related to what we heard in the media about modeling, because often modeling references were tied to changes in life, 6 feet of distancing, mask wearing, staying at home. And so that negative life change was tied to modeling. Mm-hmm. And now we're going from 6 feet to 3 feet, so the confusion still reigns. What are the top 2 or 3 sound bites that we could use in communicating with our various constituents about how lessons learned on modeling disease spread affects preparing for future outbreaks or pandemics?
Mm-hmm. Yeah, that's a very interesting question. Thank you. So, if you're talking to people, most people aren't going to understand how the model works. But I think that's why I used the example of compound interest to start off this talk, because that is something that people can understand, and they can understand that even a small change in interest rate makes a huge difference in how much money you end up with. Well, the same is true with COVID. A small change in transmission, and they might say, well, mask isn't going to do much good, or social distancing isn't going to have much impact. Well, even a small impact can have a huge impact in the number of cases. And that's what the models tell us. So that's why, we can say, well, yeah, it's uncomfortable to wear a mask, but even a small impact on transmission can be very important in helping to control the total number of cases and ultimately the total number of deaths. So I think that's one thing, thinking about. And the other thing is for people to start to understand that models are useful tools, but they're not intended to be predictions. I mean, we really can't, as scientists, we can't communicate to our community that we know the future or that we're going to tell them exactly how things are going to work, because if we don't have the data to support the models, which of course we never do at the beginning of the pandemic, we're kind of guessing based on past experience with other diseases. And so I think it's really important for scientists to communicate the uncertainty associated with our models. And much like people have become used to the idea of, the weather prediction being uncertain, we should understand that COVID predictions are uncertain. We're doing the best we can, making the best judgments, but as we learn more, those are going to change over time, and that should be expected.
Thank you.
Thank you, Loanne. Thank you, Tim. There are quite a few questions that are coming in through the chat, so if you don't mind, I'll just start bouncing those off of you. Let's start with what is the impact of different vaccination rates coupled with multiple variants that are circulating in terms of how models are adapting? It seems maybe like a battle of when you're trying to set up a model, pardon me.
Yeah, and accounting for vaccination rates in the models would be fairly straightforward, because I can create a pathway that goes directly from susceptible to immune, right? And so that's pretty easy to do mathematically. And in this case, with the vaccination numbers being fairly well tracked, we can have a pretty good idea of how many people are moving out of that susceptible pool. And that will definitely affect our predictions of infections in the future, the models can give us some idea of, how many people need to be vaccinated before, the spread of the disease is hindered significantly. So those are all very useful parts of models. But in terms of the variance, we may not have sufficient data at this point to really be able to incorporate that into the models. And so again, it goes back to the models are only as good as the data that we have to support them. As we learn more about these variants, then we can begin to incorporate that information into model predictions as well.
Cool, thank you. Several other questions related to different aspects of the model, some of which some related to those that you spoke about tonight. So in your simulated computer models, you were using hypotheticals. How were you accounting for deaths from disease? And would that change if you accounted for them differently? Or
Yeah, so in the simple model that I showed, I didn't have a pool of people who had died. I assumed that all the individuals who were infected went into the recovered pool. Really, to model the deaths case would be simply adding a parameter that would say how many of the infected people actually recovered and what proportion of them died. And so you would have to add a parameter that described the mortality rate. Again, we know the mortality rate is initially a very hard number to get a handle on. Estimates can vary widely, especially when we're not getting a lot of testing. And so we don't really know how many total cases there were. We know how many deaths there were, but we don't know how many total cases there were. So the mortality rate can vary quite widely. We now know that, we're getting a pretty good handle on mortality rates. Those are also going down over time as we get better treatments. So the models could account for that, but again, it's really only as good as the data that we have to support those kind of predictions.
Okay, thank you. Are there any compartment models of COVID-19 spread that also incorporate geographical considerations, things like transportation, travel networks, so on?
Yes, definitely. So in this case, I've assumed, only spread within a single community. Obviously, spread between communities is very important, and different timing of spread within different communities. As I mentioned, the early spread in Washington state was primarily in King and Pierce counties. But then eventually, as it made it over into Eastern Washington, we saw, large amounts of spread in Yakima County and in the Tri-Cities area. And so that changes the timing of the state as a whole. Certainly, compartments could be created for individual communities where then you would have rates of transfer in between communities. And that would be parameterized depending on how much people move amongst those communities. Initially, when we had the shelter in place, presumably people weren't traveling outside of their individual communities, but as restrictions loosened, that inter-community spread can change. And so when people are going down to Texas or Florida for spring break and then coming back to their local communities, there's a very real chance that they could be reintroducing potentially new variants into their communities, and that could have a significant impact.
Thank you. You talked about envelopes in your talk. Is that essentially the same thing as confidence intervals? And in that sense, they don't fully encompass all possible outcomes?
Yes, that's absolutely right. So they are similar to the concept of a confidence interval. And really, in some sense, the model, the envelope itself is a model of our uncertainty. We don't really know how uncertain our model prediction is, but we're kind of giving a best guess of how much of a range we might be off. Sometimes that envelope might be due to different models that we run that have different underlying assumptions. Sometimes it's the same model with different parameter sets, but in either case, we can get sort of a range of estimates. And really that reflects our best understanding of how uncertain we are about our model predictions.
Great, thanks. I think sort of right in line with that question, collaboration. So you talked, I think it was on your final slide, the importance for people to share information, collaborate with each other. You showed a nice model that was relatively hypothetical that you put together in an Excel sheet. How important is it for scientists modeling actual COVID scenarios and transmission? Is it for them to collaborate with each other? And what are the benefits of doing so?
Yes, I as a modeler myself, I am a big advocate of collaboration and openness in our modeling. And I think numerical modeling has evolved a lot over the past 20 to 30 years, from a point where people tended to keep their own codes private to themselves and not share with their community, to a place now where we have a much more of an ethos of open source software and people openly sharing. And so when you publish a paper, many of the publishers require that you provide open access to the code that you used for that model, and to the data that you used underlying that model. And I think that's really essential, not only for doing good science, but also for gaining the trust of the public and making sure that the models that we have are really the best models possible. So, again, that fits in with Justin's question. I really would be much more trusting of a paper where they openly shared their code and their data than one that didn't.
That makes sense. Great. Okay. Let's see. One of the main arguments that is that's out there about against getting the vaccine is that we don't know enough about it yet, which seems like it may stem from some concerns about something else, either intentionally malicious or unknown or dangerous about the vaccine. But is there any way modeling could help to rebut or calm some of those worries potentially?
Yeah, that's a hard question. The kinds of models that I talked about today, probably not. Certainly, the safety and efficacy of the vaccines is based on a lot of statistical models that are applied to clinical trial data. And those data are intensively reviewed by a number of boards, by the Food and Drug Administration. They bring in experts from a variety of different places and universities to make sure that those data are independently reviewed before the vaccine is released for public use. And I think that process was followed, even though it happened relatively quickly in this case. So, it's, again, a model can't by itself tell you more than you really know in terms of what the data are. But I think in this case, the statistical models are the most useful in really telling us, we did this many samples, test trials of these many people. We saw side effects in this number of people and they were mild. We saw that these people didn't get the virus, didn't catch the virus after having the vaccine, 90% of them, or whatever. Those are really important things for us to understand, that those are the things scientists are looking at carefully when they decide whether to approve it for emergency use.
Excellent, thank you. Based on your experience modeling, modeling in general, I know modeling COVID-19 is not necessarily in your line of work, but what you've been looking at and paying attention to, where do you think we might be in a year from now? We talked about predicting the future. I think it was in your flyer preview there. So let's just go for it.
Okay, thanks, Jim. So to me, I think that's probably going to depend on a couple things. If you're talking about a year from now, I think in some ways it might be harder to predict what's going to happen a month from now, because I think we're kind of in that no man's land where people are getting tired of restrictions and starting to, see the curves go back up again before we're getting fully vaccinated. My hope is that by a year from now, we will have, a large fraction of the population being vaccinated fully and protected from the virus, enough that it's no longer able to spread in our communities, and we'll see it essentially go down to a background minor problem where a few cases crop up here and there that can be contact traced. The concerns would be that not enough people get vaccinated, which would inhibit that, or these new strains coming out become resistant to the vaccine. And so in those two cases, those would be the things that would throw that prediction off as far as we know right now. So I definitely encourage people, to get vaccinated for the sake of building that herd immunity.
Great, thanks. Didn't mean to put you on the spot there as a crystal ball holder, but okay, I think we have time for one more question from the chat before we move into the closeout here. So do you have any stories or examples of modeling gone wrong? Maybe there was inaccurate or incomplete assumptions, information, related to COVID or otherwise, and how does one handle that? Are you able to recover and fix models as time goes on?
Yeah, no, absolutely. I mean, in my own experience as a hydrologist, I've experienced many models that turned out to be completely wrong, right? And for a variety of reasons. And in fact, models that had gained widespread use in the community, we later realized, well, they're not capturing a key aspect of the behaviors that we're seeing. One of the nice things about that is usually we learn a lot from that. So when we see a model go wrong, we can go, whoa, what happened? Why did that happen? Why did our assumptions, what of our assumptions was violated that caused that model to give a bad prediction? And I could give, some specific examples, but there are many in my experience. Really, the value of those experiences is to go back and look and say, what made the model go wrong? And so when we use our models in a way that we say, well, here's our prediction, we're going to make our decision and then forget about it, that's usually a mistake. We need to go back and say 5 years or 10 years later, how well did our model actually do? And was that the right decision? And if not, what can we learn from making future decisions? So, that's usually the attitude that I carry forward, is not so much worrying, was the model wrong? I know all models are wrong. The question is, what can we learn about why it went wrong and how can that help us in the future?
Perfect. That's a great answer. Thank you.
Mhm.
Okay, well, thank you very much, Tim, for the talk tonight, for taking the time to share your knowledge and answer the questions we've had here. I think it's time to move on to the closeout. I'd like to close this seminar series down with a big round of thank yous. Take me a couple moments here. So first of all, I'd like to thank everyone here that's tuned in. Tonight's seminars, the previous four seminars, really appreciate the audience, the community engagement, and I do hope that you enjoyed and learned quite a bit from these talks. I'd also like to give a very special thank you to our community representatives for participating in this 5-part series. Loanne, Kate, Martine, and Justin, it's been wonderful to interact with you guys for the last 5 weeks. I know that schedules are tight. Dedicating one evening can be tough, so 5 in a row, that's very great. I'm so excited or so happy that you guys were able to join us the whole time. If you're willing, I'd like to give you each a moment to say a few sentences, maybe about some of your major take-home messages, things you've learned from this seminar series, if possible. So let's start with Kate. Anything that stood out in particular to you?
Yeah, I think I've been able to take some of the information that I've learned in this series into my work, especially as we're talking about reopening plans for fall. Everything from Dr. Wiley's description of the movie theater and, how that might be less, there would be less transmission with people sitting in a lecture style rather than at round tables, to Katrina's discussion about 3 feet versus 6 feet, how it's, applicable probably to elementary, but maybe not high school and colleges. So yeah, I've been using a lot of what I've learned in my work every day. Thank you.
Great. Yeah, great. I'm happy to hear that. Justin, how about you?
I'm a choir director, and over a year ago, our industry was among the first that were impacted by this pandemic. In fact, one of the first large outbreaks of the virus was a community choir on the west side of our state. So I have been very reticent to re-enter this arena. Actually, a couple of weeks before this series started, my organization began conversations about how do we transition back to having rehearsals and concerts. So I certainly feel like I have a much more comprehensive understanding of the virus and mitigation techniques. I feel much more confident going forward in the next few weeks that I'm going to be seeing my singers together in person. And I'm just so grateful that we have these local experts here in our backyard that we can rely on and who are willing to give their time and talents to help educate the community about something that has been very complicated from the start, knowing that this was a novel virus. So thank you to the team for the invitation. It's been a pleasure to be a part of the panel. Thank you for equipping all of us so that we feel a little more confident going forward as we resume activities and try to get back to normal.
Thank you, Justin. Martine, we'll move on to you.
Hi, yeah, thank you, Jim, and thank you again for doing such a great job facilitating these last 5 years. Looks like you might have another career there other than science. So I think for me, the most important thing was kind of just relearning about the importance of science and research and the understanding of both the virus itself and the vaccine, and then taking that and trying to apply it in my 2 roles, both in higher education and working with small businesses and the Latino community, and sort of sharing that information, that knowledge to help folks make better choices with educated sort of decisions and with research, et cetera. So it's been really great to have that knowledge, and really thank you, PNNL. Thank you to the 5 researchers who share their time and put so much work into educating us about this and making us better citizens for the community.
Thank you, Martine. How about Loanne?
You know, 2 things that really have come to the forefront, learnings from this interactions over our 5 weeks that I've been sharing over and over again. And that's really about the different types of vaccines and what they mean and don't mean, and the different types of tests and what they mean and don't mean. And I think what has been really important is that we have renowned experts here who are really deep into the science. But more important, we put a face on the experts because they live right here. They're growing their careers and their families right here. So they're real. And they aren't just some expert far away. So I think that element of bringing science directly to the people and in a language you can really understand is just super important. And I really compliment the team because you did demystify COVID for so many people. So thank you.
Thank you. Thank you, Loanne. Thank you to all 4 of you guys for joining us again. That's been great interacting with you. It sounds like it was an informative seminar series that benefited you in different ways. So I'm very glad to hear that. Next, I would like to thank all of our speakers. So Steve Wiley, Amy Sims, Katrina Waters, Kristen Omberg, and Tim Shibey tonight. Thank you guys for sharing the science of COVID. We started off with a nice high-level overview related to what we know so far about COVID, and we got into some more specific details related to symptoms of the disease, transmission, vaccination, prevention. Tonight, talking about modeling and how that works. So this was a really great series, and yeah, again, thank you to all the speakers for your time. Finally, I would like to thank the team of behind the scenes PNNL community affairs and communications experts who have made this seminar series possible. There's a lot of people who have been working very hard over the last couple of months to make sure that this series ran smoothly and without any hitches, and they've done an outstanding job. I'd like to personally say thank you for giving me the opportunity to serve as the moderator here. I've really enjoyed it. I think I caught Martine in a slip of the tongue there saying it's been the last 5 years. I probably look like I've aged 5 years, but it's really only been 5 weeks. It is not due to stress related to this seminar series. I have a daughter who's turning 6 months old today, actually. So 5 weeks in my house is about the equivalent of 5 years. But honestly, my job here as a moderator has been made extremely easy from the work of our team behind the scenes. So thank you guys. I would like to just take one more chance to remind everyone that there will be a brief survey after this. If you've attended, if this is your 5th, if you're 5 for 5 and you complete the survey tonight, you'll get the digital certificate of completion. The link to the survey is in the chat window, and it should also just pop up automatically when you close Zoom. The recordings of these talks are being posted. The previous 4 are already posted. Tonight's will be posted soon. They're on PNNL's Demystifying COVID website. The link is in the chat. It's also the same link that same place you found yourself when you were registering for these events. So I encourage you to find these recordings, share them with friends and colleagues who might not have been at the talks. As we move back into the regularly scheduled seminars that are part of the Community Science and Technology Seminar Series, please remember to visit the link in the chat to the PNNL events webpage. This will take you to a site where you'll be able to find information about upcoming talks. The next talk that we have scheduled is in a couple of weeks on April 13th. We'll hear from Vijay Murugesan on batteries beyond lithium. We're also providing the Zoom registration link in the chat window to that talk. So to finish this series off, I would just like to hand the mic over real briefly to a member of PNNL's leadership team who sponsored this effort. Mullen Young is the Associate Laboratory Director for the Earth and Biological Sciences Directorate. It's a research arm here at PNNL, where some of the speakers featured in this series work, including myself and Tim tonight. So Mullen, why don't you share your thoughts and close us out?
All right. Well, thanks so much, Jim. I just wanted to echo some of the thanks that you've already given. I want to thank Tim and the rest of the speakers for a really excellent series of talks on COVID. I want to thank you, send a big thank you out to our community representatives, everybody who was working to put this together in organizing this series. And then, of course, I want to thank everybody who dialed in to join us here. It was really, I think, important for us to have this opportunity to share our science with you. Not only are we excited just to talk about science and share our results, but it also gives us a sense of, what are you thinking, and what are you, what are your questions, and how can we address some of the, I guess, open issues that may be out there regarding COVID. So, we've really enjoyed having this discussion with you all. And also, these kinds of interactions really show us the kind of positive impact that our science can have on our community. And so I just want to thank everybody from our local community here for dialing in. But I was also, really impressed by the number of people from around the country who have joined us here tonight. I just want to close by, inviting you to invite friends and family to go to the Demystifying COVID website to check out our talks. And I wish you all a very safe and happy Easter weekend. So thank you.
Looks like it's just us now. Great job tonight.